Okay, so special relativity. Einstein thought to himself, I wonder what would happen if I were riding in a train car and that train car were moving at the speed of light. So this is the question that we all asked ourselves. What would happen if we were moving at the speed of light next to a photon? So he said to himself, all right, well, I know that a photon is an oscillating electric and magnetic field and that they satisfy Maxwell's equations. And so, okay, here we go. So here is my train car, here is me, and here is this, well, okay, that's him like this, holding something in his hand. And here is the electromagnetic wave that is propagating along with me as I am driving or riding in this train car. And so you have your magnetic field that goes like this. You have your electric field that goes the other way. So the electric field goes up and down. The magnetic field, in this case, goes side to side. And he was saying, if I was going along at the speed of light, then this would be a stationary structure. You would have this wave, and I would be traveling along with the wave, and so I would see an electric field that points up here and down here and then back up again, and it would just be static. It wouldn't be oscillating. And he said to himself, well, this can't be true. This would violate Maxwell's equations, because Maxwell's equations say that the only way to have a standing electric field like this is if you have a charge that's creating it, and there's no charge here. And the only way to have, so in order for the electric field to propagate, you have to have this interaction between the electric and the magnetic field that are contained in Maxwell's equation. So it's this, what, dE, dt, squiggles, the curl of B, something like this, that's a cross. And then you have dB, dt, so the time-changing electric field, the time-changing magnetic field, they squiggle del cross E. The curvature, or the curl of these two fields, one of them has a minus sign, I think it's this one has a minus sign. So this requires that if you want to have a magnetic field in a given location that's pointing in a given direction, you have to have this oscillating electric field. The electric field has to be changing with time, unless you have a magnetic charge or a magnetic field that, like a north or south pole, that's sitting there, or an electric charge that's sitting there. And since there's no electric charge sitting here, you wouldn't be able to have a static structure. It has to oscillate because it has to use this part of Maxwell's equations. So because you have to use that part of Maxwell's equations, this implies that the electric and the magnetic field must be wiggling. And if they must be wiggling, then they must also be traveling at the speed of light. So because you put these equations in, you get out a bunch of constants. I think it's 1 over the square root of the permittivity and the permeability of free space. This is a mu, by the way. It doesn't look like a mu, but that's what it is. So I think this is the speed of light. And those are constants that come into these equations. And so because the equations must wiggle, they must propagate at the speed. And therefore, it doesn't matter. Einstein concluded that it doesn't matter how fast I'm moving. Any photon that is traveling by has to be traveling at the speed of light with respect to me. If it changes, if I can travel close to like at the speed of light or beyond the speed of light or slower than the speed of light, and the photons outside are traveling slower than the speed of light with respect to me. So like say I'm going at 0.9 c, and naively one would assume then that these photons would overtake you at only 0.1 c, 0.1 c, not 0.01 c, 0.1 c. Hold on, I need to rescale this a little bit so you can see all of the parts. So one would assume that if you're traveling at 0.9 c, then the photons would be traveling at 0.1 c next to you, but this can't happen. This is not allowed because that would violate Maxwell's equations. And so Einstein concluded, I must not be able to travel at the speed of light. No matter what happens, if I'm moving in some direction, light must always travel at the speed of light with respect to me. If that weren't the case, then I wouldn't, like all the electrons in my body would stop functioning, right? All of the chemical bonds would stop functioning. So, question, should I see this photon as you've drawn, should it see it as 2 points? So the photon, well, this is a light wave that's propagating at some rate, and it's a sum of an electric field. So here's the electric field that's oscillating up and down, and you have a magnetic field that's oscillating side to side. So that's what I tried to display there. So that's what's going on. So these are not individual photons, but these are the waves of the electromagnetic wave as it's moving there. So that means if you're traveling at the speed of light, a photon will still pass you. No, so what it means is that you cannot travel at the speed of light. because then a photon would not be able to pass you. And so you must be traveling less than the speed of light, and photons must always be traveling faster than the speed of light. I'm sorry, I lied. Photons must always travel at the speed of light with respect to you, no matter what reference frame you're in. So you can boost to any reference frame you want, but that reference frame, to be physical, that reference frame must always be traveling slower than the speed of light, so that the speed of light will always be constant. And what this implies is that if you have a coordinate transformation, so say you have, here's one coordinate system, like this. Here's a coordinate system, and the speed of light, here's a photon going by at the speed of light. If I transform to another coordinate system, like this, so here's another coordinate system, and this one is moving, like that, there has to be a way for me to add, like to transform from this coordinate system to this coordinate system. It's called a Lorentz transformation. And when I do that transformation, this photon must still travel at the speed of light with respect to this coordinate system, no matter what. What this implies is that you actually change the way that you add velocities. So it doesn't mean that, well, it basically just changes the law of addition, the laws of addition that apply in relativity. So let me answer this question. Question coming up: if you go to the limit, yes. So if you're traveling here at 0.999999999 c, so that's pretty fast, then this photon, or this photon, either of these two photons, will still travel at c with respect to you. So let's put up an example, and this is kind of the traditional example that people use. So here's me on a spaceship. It's a big rocket ship like this, and I'm going to stand on this rocket ship, and I'm going to throw a baseball, and I'm a very good baseball thrower. And so the rocket ship might be moving at like 0.8 c, and the baseball might be moving at 0.8 c with respect to me. And so the question is, how do I boost into the frame of this baseball? Like, how fast is this baseball moving with respect to the outside observer, I guess is another way to put it. Well, that's a really unusual outside observer. Let's try this again. There we go. There's my outside observer. So the outside observer sees the spaceship traveling at 0.8 c with respect to him, and the baseball is moving at 0.8 c with respect to me. And so how do I transform to the reference frame him? How fast is this baseball moving? So I need to add these velocities together. And so I need to add these two velocities together. And the way that I would normally do it is I would say, oh, well, the total velocity of the baseball right here is going to equal the sum v ship 1 plus the velocity of the baseball 2. So we'll call this one v2, and this one here v1. So v2 plus v1 is the way that you add that. And all that you have to do in special relativity to make sure that, so the problem with this is that if you add these things together directly, then you get v total is 1.6 c, which is faster than the speed of light, which would cause everything in the universe, at least that interacts with the electromagnetic field, to cease to function, which would be a bad thing. We don't want that to happen. So this can't be true, or this can't be correct, because it allows this object with mass to travel faster than the speed of light. So all you need to do to fix this is that you change this to circle plus, like that. So now the plus has a circle around it, and that fixes everything. So you need to have a new rules of addition that are this circle plus right here. Now they don't use this notation in physics textbooks, but they probably should. That's my opinion, so they should. We have this issue where we have to start with a total velocity is equal to v1 circle plus v2. And we need to have, this circle plus is going to have definitions, has to have a new definition that when you add these things together, you always get a number that is less than the speed of light. You always have to get a number that is less than 1. And so it turns out that there are a variety of ways to do this, and there's one that's right. So the way that you add these different velocities together is that you say that the v total, now we're going to use regular addition, is going to be v1 plus v2. So this is regular addition here, divided by 1 plus v1 times v2. Okay, and then v1 and v2, this is some number times the speed of light. So you should have in here like a divided by c squared, but v1 is actually the velocity divided by c. v2 is also the velocity divided by c. So that way you can just ignore the c's. But technically you should have a over c squared in the denominator down here. But it muddies up the formula to have that in there. Okay, so go ahead and ask your question. So this is the velocity addition formula. This is how you transform from one reference frame to a separate reference frame, where those two reference frames are moving. Here's a question. What happens if you apply a force traveling at the speed of light? So there's nothing that can travel at the speed of light. So there's no... okay, so I'll get to that actually. The question is, what happens if you apply a force traveling at the speed of light in the direction of motion? So let me rephrase your question in a way that you can actually have happen. Suppose that you have a particle that is moving close to the speed of light, and then you apply a force to it. And we will get to that in a little bit. Okay, so this is the velocity addition formula. And let's take an example of how this would work. So if you have V1 is going back to that baseball thing that we had, I'm going to change the speeds a little bit. Let's say that V1 is 0.9 c. So 0.9 and V2 is also 0.9. Then if I add it using this formula, I'm going to get V total is equal to 0.9 plus 0.9. These are all measured relative to c. And then 1 plus 0.9 times 0.9. And so that's going to be, I need to make sure I'm not, so that's going to be 1.8 in the numerator divided by, and it's going to be 1.81 in the denominator. That doesn't look like an 8, but here we go, 1.81 in the denominator. So 1.8 in the numerator, 1.81 in the denominator, and you'll notice that the numerator is smaller than the denominator. So this quantity here is less than 1, so it's less than the speed of light. So this is the velocity addition formula that you have. This is how you add velocities. When you're transforming, like you have one object moving with respect to you, and you have a second object moving with respect to the first object. Then what is the total velocity that you measure of that second object? So the first object is moving with respect to you, the second object is moving with respect to the first object. How do you get the motion of the second object with respect to you? You add the two velocities together using this formula. So there are a number of waves. Okay, so it's a little bit weird that there's this strange addition formula, but there are other ways that we add things together that are just as strange or even more strange than this addition formula. And so it shouldn't be too much of a surprise. I guess it's a little bit of a surprise that in the physical world, we add things together like this. But let me show you two different ways of adding stuff that everyone should be familiar with. So let's say that I have AB, and I'm going to add to it CD, like this. I'm going to add these things together. Okay, so there's a couple ways I can do this. One of them is to go like this. A plus C, and then B plus D, like that. So this would be the way that you add ordered pairs. So if you have, XY coordinate and another XY coordinate, when you add them together, you add them together like this. You add the X coordinates together, you add the Y coordinates together. Another way that you can do the same thing, A, B plus C, D. Another way to add these things together would be to do it in this manner. AD plus CB and BD, like this. Okay, and this way of adding things together, it looks more strange, but you'll find that it has all the properties that you expect it to have. It's associative, it's commutative. You can so you can add these in any order that you want. You can group them together and add them together like one pair at a time if you have a third thing that you need to add into this system. It has inverse elements. It has the equivalent of a 1. It has the equivalent of a 0. But there it is. This is what the formula looks like. This is the formula that you have when you add fractions. So if you have like a 1/2 plus a 2/3, this is how you add those things together. You find a common denominator. That's the product of these things down here. So the common denominator is this product. So that would be 6. And then you multiply this thing by what's missing. So that's this thing by the missing part, which is a 3. You add this, multiply this one by what's missing, which is a 2. And you end up with, so this would be what? 3/6 plus 4/6, and that gives you 7/6. Okay, and that follows this formula. So there are different ways of adding things together that we already familiar with. That's different than the way you would normally expect, adding 5 plus 3 together would be. And so when you're adding velocities in different reference frames with moving objects, that's the way that things add. That's the way that the universe forces you to add them in order to preserve something moving at the speed of light to travel at the speed of light with respect to you. So let me give you an example. Suppose you have something here that's moving at, like you have a spaceship. And this is a person that's holding a flashlight. So here's the spaceship moving at 0.9 c, and here's a flashlight here moving at c. Okay, so here is a, let me go over some questions real quick. There's a question. There's a lot of questions here. You can describe an object moving faster than the speed of light, but if you transform to a different reference frame, then it must always move faster than the speed of light. I'll get to that in a minute as well. Okay, so first of all, you can't have v1 be positive 1 and v2 be negative 1 because that implies that they're both moving at the speed of light. Let me do this example, and then I'll do some of these other cases. All right, so here we go. Ready? V total. What is the speed of the light with respect to me, the outside observer? So here's me, the outside observer. Here's this nefarious person who's shooting a laser beam ahead of him as he's riding on this spaceship traveling at 0.9 c. Okay, so what I should be doing is 0.9 plus 1 divided by 1 plus 0.9 times 1. Okay, so this is that velocity addition formula that I had there. And what do I get? I get 1.9 divided by 1.9, which is the speed of light. So the speed that this laser beam is moving with respect to me down here is the speed of light. So it doesn't matter what reference frame. This could be anything, right? This could be any number. That could be 0.8, and then I get the same thing, 1.8 over 1.8. So anything that's moving at the speed of light will be moving at the speed of light to every observer. Every observer, no matter how fast they're moving with respect to this object here, provided that it's in our universe where you can only travel at the speed of light. Anything going slower than the speed of light will always be traveling slower than the speed of light. Now, what this corresponds to, if you were to plot, let's try that again. If you were to plot like position versus time, I think this is like the time graph, time in this direction and position in this direction, and you have some position like this. So here's your location. Transforming to a different reference frame places you on a hyperbola. It looks like that. So as you transform to a different reference frame, then you get the velocities add along a hyperbola like this. Or the events that you have will transform along a hyperbola. And so you can only, because you can only transform along a hyperbola, you will never get to the point where the slope is equal to 1 because this asymptotically approaches 1. So the slope of this hyperbola is always less than this asymptote. So hyperbola has two asymptotes. They come in like this, okay, and it asymptotically approaches that, but it never crosses it. And so when you do these transformations, it moves you along this hyperbola, and you never actually cross the the asymptote. And so the slope of this line, that slope is always going to be less than the hyperbola, and so the velocity will always be less than 1. If you have some object that magically were able to travel faster than the speed of light, and so that would correspond to something on this side of that asymptote, then when you do the same Lorentz transformations, it will only be able to transform to something on that same side. So the transformation here to an object that is moving faster than the speed of light, it will always move faster than the speed of light in every reference frame. So you can move to any reference frame and it will always be traveling, it will always have a slope that is tipped over further than 45 degrees here, because this line here corresponds to the speed of light. Okay, so these objects, an object that's out here, they've never been discovered. They would be called tachyons if they were discovered. Tachyon. So a tachyon meaning like a tachometer, a fast-moving thing, a thing that measures how fast something is moving. So tachyons, that's an A, by the way, are hypothetical objects. They've not been measured that travel faster than the speed of light. And if you transform to a different reference frame, it always travels faster than the speed of light. So, and the Lorentz transformations, the way that you transform from one coordinate system to another, never allows you to cross over the asymptote. And so these are totally separate worlds. You can't get a tachyon to come back over into regular particle space and vice versa. Let's see. If you take a giant screen and shine a light on it, illuminates it, now you move a finger before you light, the shadow can travel. So let's see, I think. All right, are there things that move faster than light? The answer is, well, none that have been discovered. So as far as we can tell, no. So these tachyons have never been discovered. If they did exist, this is their transformation properties, the transformation properties that they would have, but they've never been discovered. Let's see. Okay, now what happens if you take an object and you exert a force on that object? So here's an object, and you exert a force on this object. Star Trek in the 90s. Oh yeah, so there were some tachyons that were discovered in Star Trek in the 90s, but don't forget that Star Trek takes place in the future, and so you have to. The discovery hasn't happened yet, even though it was predicted that they would be discovered in Star Trek in the 90s. The discovery hasn't happened yet. We have to wait until whatever 2165 or whatever the things are. Okay, so with you have this object. It's got some mass, and it has some momentum. If it's moving, it has momentum. So the momentum of an object is this quantity right here, mv. And this isn't entirely true. When you have an object moving in a, so if you're considering special relativity, this isn't the way that an object, this isn't the momentum that an object has. Instead, because you have to consider this velocity addition formula, momentum is actually given by the quantity gamma mv. Okay, gamma mv is momentum in relativity. This gamma is the thing that accommodates the fact that you're adding these velocities, and you have to use that velocity addition formula to properly get to your next velocity. As you add energy to the system, or you add momentum to the system, now you're moving more rapidly. You have to say, oh, I'm moving more rapidly. Here's the velocity addition formula. And so when I add up each change in velocity that I get because I'm exerting a force on it, I have to include this factor gamma. That's basically where this comes from. There are other places where this pops up. You can derive it in different locations, but we're going to use this here for now. So momentum is actually given by gamma mv, not by mv itself. And so if you apply Newton's second law, here's this object, I'm going to exert a force on it. Force, Newton's second law says that forces cause a change in momentum. Okay, forces cause a change in momentum. All right, so that means I'm exerting a force, and that's going to cause a change in gamma mv. Okay, the mass is a constant that's going to come out front. There are some books and even some people who say that relativistic mass is this blah, blah, blah thing, which is total garbage. That is not what happens. You have a mass, that mass stays fixed. What changes is velocity. Okay, these are the things that are actually changing. The mass is a constant thing. There's no relativistic mass. There's mass, and then there's how a force affects the velocity. So you're looking at the change in gamma mv, and as you increase the velocity, this gamma is what keeps this is the thing that grows. So gamma as a quantity is 1 over the square root of 1 minus v squared. Let's see, do that a little better. 1 minus v squared. This is all measured with respect to the speed of light. So if you ever see a v and you want to put it in meters per second, you have to divide by the speed of light to get the units to work out right. But we're going to use units where the speed of light is equal to 1. And so this gamma 1 minus v squared, what's happening when you're exerting a force on something is here's your force, and you're causing a time derivative change, ddt, of gamma v, which is v over the square root of 1 minus v squared. Okay, this is the thing that is affected by the force that you're exerting. And when you continue to exert that force, this quantity here will grow. It grows without bound, but the consequence is that v will always be less than 1. So, yeah, and so you mentioned, isn't v squared over c squared? Yes, I mentioned that, but I also said that c is equal to 1. So if you ever see v, that's equal to whatever your velocity is over the speed of light. So these are, this is what changes. The mass stays fixed, and then you get a change in velocity like this. Okay, so let's take a look at where this gamma comes from, this 1 minus v squared, or yeah, 1 over the square root of 1 minus v squared. Here we go, ready? And this goes into the basics of special relativity. Some of the stuff we kind of jumped ahead of ourselves a little bit. Now we're going to go back and derive this quantity, but I thought the velocity addition formula, it was a new way to present it, and so we presented it that way. Okay, so here you have yourself a train car, and you have a person in that train car, and you have a special clock in that train car, and that clock is a light beam that is bouncing up and down between these two mirrors. And so one tick of the clock is the movement of that light beam from here up to here. We'll call that one tick. You could have it be a full cycle or whatever. If this train car is moving, then you're going to get something that looks, well, with respect to you. So the person in here who's stationary, this person who's stationary with respect to the clock, they measure what's called the proper time. So this one gives you the proper time, which is T naught. I will denote it by T naught. If you are stationary with respect to the clock, then you measure the proper time. The person in here in the train car, standing next to the clock, measures the proper time, which is the amount of time that takes, the amount of seconds, the number of seconds it takes for the light beam to travel from one mirror to the other mirror. On the other hand, if I'm standing out here and I'm watching this train car go by, so I'm going to draw it up here. Here's the train car going by, and there's a person standing in there. The person measures the proper time who's standing inside the train car. Here is that clock, like this, and this train is moving with some velocity. Then I'm going to get, this is what I see on the outside. Pretend that that's straight. Right, that is the trajectory that I see for that photon. The photon's moving up at an angle so that it hits the mirror down here at the bottom and it hits the mirror up here at the top. Okay, so now you have to say, well, this is the time that I measure. That's the time that I measure. The proper time is what the person inside measures. The person inside just sees the photon move from the bottom to the top. And so you can come up with here's the proper time right here. Here is my time that I measure, the dilated time, and I've got this velocity. Okay, and then you just add up the components. This thing here is going to be the sum of the squares of this portion here, this part of the triangle. Here's a triangle, here's a triangle, or here's one leg of the triangle, here's the other leg of the triangle. They're perpendicular, and so the sum of the squares of the sides is equal to the square of the hypotenuse, and you end up with the proper time, which is the dilated time, which is what I measure. So I measure time t, I'm the outside observer. It's going to be equal to gamma times the proper time. Gamma times the proper time. So let's see if we can show a little bit more detail about what that looks like. So that implies what? So this is going to be t is equal to gamma times the proper time. I'm going to multiply this out. I'm going to get a t squared times 1 minus v squared equals t naught squared. Right, so that's because gamma was 1 over the square root of 1 minus v squared, 1 minus v squared, like this. This is an equal sign. And so I'm going to square both sides, and I'm going to multiply this up, and then I'm going to get a t squared minus v squared t squared equals t naught squared. And then I'm going to go t squared, which is the hypotenuse. The hypotenuse was equal to t naught squared minus t squared v squared, like that. Okay, so if I wanted to put plus. If I needed to put the c's in there to make all the units work out correctly, then this would be over c squared. Okay, so this is the vertical component. Right here was that triangle that I drew. I was trying to get this length, which is a time, and the time here is going to be wait, what am I missing? Am I missing something? I screwed it up. 1 over 1 minus. No, this is right. So 1 over the square root of 1 minus v squared. Yeah, okay, so this is right. So this component, this t naught over here, that's t naught. This is t, and this here is that length. This is t times c, this is t naught times c, and this is v times t. Let me try that. Let me try that one more time. We're going to do this one more time, so that I probably should have started by putting all the C's in there to begin with. Okay, here we go. Here is the train. Here are the 3 legs that we're looking at. This is the time that I measure from the outside. Here's me, the outside observer. I'm measuring this time. And this is a photon. The photon travels at the speed of light, c. So that's the length here, is the time that I measure and the speed of light. Oh, there. This length here is the proper time times the speed of light. It's the speed that the photon takes to get from the bottom of the thing to the top of the thing. That's what the person in the train car measures. This one here is the time that I measure, because it's me, the outside observer, that actually watches this thing move from one place to another. Time that I measure times the velocity of the train car. Okay, this is what I should have done from the beginning, but now I did it. Okay, so now I can do my Pythagorean theorem. T squared c squared equals t naught squared c squared plus t squared v squared, like this. I can divide by c squared. I get t squared equals t naught squared plus t squared v squared over c squared. That's what I had on my previous one. I move this over to the other side. I factor out. I get t squared equals, t squared times 1 minus v squared over c squared equals t naught squared. Okay, and then I take the square roots and I set c equal to 1, and I get what I showed you the first time, which was that t is equal to gamma t naught. Okay, so I had done it correctly, but I had confused myself by not doing it like this correctly. Okay, so there we go. So this tells you what? Well, gamma is always a number that's bigger than 1, right? So you have 1 over the square root of 1 minus v squared over c squared. V is always less than the speed of light, so this is a quantity that's always less than 1, which means that this denominator is always something that is less than 1, because you have 1 minus a number that's, whatever this number is. It's usually given by beta, beta squared, although that's kind of silly. So this thing here is always less than 1, and so 1 minus that is always less than 1. So I have 1 minus this thing. This is less than 1. I have a 1 over a number less than 1. So less than 1 here, which means that this is always a number bigger than 1. That ratio is always a number bigger than 1. I have a number smaller than 1 in the denominator, which means that the total fraction is always bigger than 1. So that means what? That the time only gets longer. The time that I observe only gets longer than the proper time. The proper time, again, is the person standing at rest with respect to the clock. The time that I measure is called the dilated time, which is how when does the clock tick by a certain amount? How many of my clock's seconds does it take to see 1 second of the moving clock? That's what's going on. We can see kind of how this would work. For example, well, let me do what happens with length, and then there's a good thought experiment that shows you why the length has to do what it does. So if the time is going to spread out, then lengths also are going to be adjusted by this. So if you measure something's length, like here is a giant candy bar, and I want to measure its length, I would hold a ruler up to it. So here's my ruler, and I hold it up. If I'm standing at rest with respect to this candy bar, then I will measure what's called the proper length, L naught. So the proper length is the length of an object that I would measure when I can lay my ruler down next to that object and measure both ends of the object simultaneously. So if this thing is standing here, I lay the ruler next to it, I measure simultaneously both sides, I get the proper length. If this flying candy bar is moving with respect to me at some speed v, then what's going to happen? Well, if I'm down here and I'm looking at this candy bar and I hold my ruler up, I don't actually measure both sides of this thing simultaneously. So I hold my ruler up to the sky like this, and I measure this candy bar as it goes by. The problem is the light coming from the back end of the candy bar is going to travel like this to me. The light from the front end of the candy bar is going to also travel like this to me, like that. So I'm going to measure this length, whatever that length happens to be. However, notice that these two lines are not the same length. This line is not the same length as this line. And since the photons leaving the front end and the back end of the candy bar are traveling different lengths, they don't arrive at me at the same time. So if I'm holding my ruler up and I'm trying to measure something relative to my ruler, I need to have light that comes to my eye at the same time, that hits my eye at the same time. That means that the photon that leaves the front has to leave at a different time than the photon that leaves the back. So I have to set something up that looks like this. So here is my flying candy bar. I'm going to set up two different frames of its motion. So there's one frame of its motion. I'm going to set up the second frame of its motion slightly offset. So here's the second frame of the candy bar's motion. Okay, so if I'm down here and I'm measuring, I'm holding my ruler up like this, and I want to measure the side, what I'm going to measure is the front end is going to come from this frame like that, and the back end is going to come from this frame like that. And so I'm going to measure light that actually was emitted by this candy bar at two different times. And so what I see, and at every point along this way, it's going to be light that's emitted at a slightly different time. So what I'm actually going to see is a candy bar that is shorter. So instead of so I'm going to see a candy bar that's shorter because here's the back end of the candy bar and here's the front end of the candy bar, and notice that it is not the same as the length of the candy bar. The thing is shorter because I need to see light that arrives at my eye simultaneously from the front and the back when I make my measurement. So the length that I measure, L, is going to be different than the proper length, which is what I measure when I'm at rest with respect to the object. And so that is L is equal to L naught over gamma. If you work out the geometry, you get something like this. So lengths contract by this quantity gamma, and lengths contract by that quantity gamma, and time grows by that quantity gamma. Okay, so here are some questions. Talking about candy, yes. Why does it have social eating? Is it because we're talking about candy bars? That's why social eating is the game tag. I try to find new tags to film these streams with. Let's see. Can I draw the graph for gamma? Yes, I can draw the graph for gamma. I will do that in a moment. What is the thing about you can't measure the speed of light? Okay, so there was a video that was put out by Veritasium where he says that you can't actually measure the one-way speed of light. And the reason is that all of the measurements that we make of the speed of light imply both a forward and a backwards. You measure a round trip time and then you time it that way. But we don't actually measure a one-way light travel time because, we can't have a detector that travels along with the photon that we're emitting. So you emit light, you send it one way, and you bring it back the other. And there have been a number of discussions about possible experiments that one could do to try to measure a one-way speed of light, but it hasn't been done. I don't know how seriously people worry, how much it's worried about in the circles of people that would measure this. I wonder if, I guess that would imply you can't measure the speed of light in a vacuum. I wonder if that's a real concern because you can measure the one-way speed of light when you're not in the vacuum. It might, well, let me give you an example. So we'll come back to this length contraction and stuff here in a moment. So measuring the one-way speed of light is a concern, something that's come up in a number of situations. The people in the office next to me are talking kind of loudly, so I'm going to turn on some ambient noise to hopefully drown some of that out. If you have, at Fermilab, they have a particle accelerator. I'll pull up a map of this. So if I go to Fermilab, map. So I'm going to go to Google Maps like this. Here is the Fermilab entrance. Wow, this is taking forever to load, but it's okay. We'll get there. Here's the Fermilab entrance. All right. And now I'm going to, this is the main entrance. You come onto the Fermilab campus, and you have here, this is the main office building. And this thing right here is called the main injector. So the main ring, this is the main ring. This is the main ring, and then this is the main injector. The main ring was built in the 70s. And was all fancy and nice at the time. The main injector was built, I think, in the 90s to do other measurements like the top quark discovery was the main reason that this was built. Anyway, so this is an accelerator that delivers a beam into the main ring. So the main ring is basically closed now. They don't use it anymore. But there was a ring of magnets in here. Then you would send the particles around to smash into each other at the detectors at D0. This is the D0 building. And this was at C0 at the time. Now they've got a new building built on top of it. So anyways, this is a 1 kilometer radius ring, and it had a bunch of magnets. And when they made the Tevatron, it was in order to get faster moving particles, they had to inject them in at a higher speed. So instead of just accelerating the particles and then putting them in here and accelerating it around this ring, they had to build up the speed first and then inject it into the ring, and they had stronger magnets in order to curve them around. So they went from having conventional magnets to having superconducting magnets in the Tevatron. Same building, but different magnets, and so a different instrument. Okay, so the main injector is right here, and you'll notice that it's kind of kidney bean shaped. Part of the reason that it's kidney bean shaped is they have this beam of particles coming in. It's a beam of protons and antiprotons that are circulating around, and they're going to shoot them into the main ring. But the beam shape is going to be different, right? It's a bunch of particles that come spewing out of a fixed target. You have a fixed target, you bombard it with something, and out come a bunch of particles, and those particles are going to be moving in a variety of directions, and you need to trim off and shape the beam so that when it gets injected into the main injector, you know what the profile, the density profile of those particles looks like. So that you know it's concentrated in a given location, it spreads out a little bit on either side, but it's not, the particles aren't going in a bunch of wild directions. So you need to trim condition the beam. You need to take the existing beam and kind of force the particles, shepherd them into a nice tight bunch. And that's done in the main injector. And the way they did that was they measured the beam properties on one side of this ring, and then as that beam is coming around, they would send a signal along here to the other side, and then they would adjust a set of magnets on the other side that would cause particles that were too deviant to be peeled off. And so they could send a light signal across this gap in the amount of time that it took for the particles to travel around the gap, like around the perimeter. And so to some extent, it's not really a one-way measure of the speed of light, but it's a constraint on the one-way speed of light. So that video by Veritasium where he's like, you can't measure the speed of light in two directions, you can certainly put constraints on it. You don't measure it directly, but you put a lower bound on what the one-way speed of light is by having a setup like this, where you have particles that are traveling at like 99% the speed of light, and you have a beam of light that comes across here. That beam of light, it's a foot per nanosecond, and so you accumulate, maybe this is 1,000 feet, so you accumulate a microsecond that you can use to adjust. A microsecond is like a megahertz. That you can use to adjust the magnets over here and shape the beam in some way. So there's that. Okay, so let's see. Are there any plans to build a new particle accelerator in the US anytime soon? Not anytime soon, but there are designs for new accelerators to be built in the United States. It's just that they're not, right now there's no reason to build one because we don't know what to build it for. So there's a question, why does it not look circular? It doesn't look circular. I don't know all the reasons why this was designed the way that it was with this particular shape. Probably because there's a train track that runs right here, and so they had to fit it into the train track. And so they just took this thing and shaped it the way that they did. So I don't know all the details about that design. So there we go. All right, so now there was another question, going back to what we were talking about here. Another question, which is, what does gamma look like? Gamma, which is 1 over the square root of 1 minus v squared. Again, the speed of light is equal to 1. What does this look like? So here is gamma as a function of velocity, and this is the speed of light, v equals 1, right there. Gamma looks like this. It goes like this, and then it goes really fast, really steep like that. It never crosses that line, but because the best you can do is get really, really close to 1, and so you get this thing really, really close to 0. It blows up, but you never actually get to velocities less than 1, or velocities greater than 1. And so as a consequence, this becomes imaginary. So you get this asymptotic behavior up like this. Okay, so that's the shape of gamma. We've seen length contraction and time dilation. So when you have a clock that's moving with respect to you, that clock will appear to slow down. when you have an object that's moving with respect to you, it will appear like, let me rephrase that. If you have a clock, here's a clock right here that's moving with respect to you. Here's me. This clock will appear to move slower than if that clock were in my own hand. So this clock will advance more slowly than this clock will from time dilation. Okay. The width of this clock here would also appear scrunched. So the clock would look like an oval moving in this direction instead of a perfect circle. If I was standing next to the clock, it would be a perfect circle because all clocks are perfect circles. But if it were moving in a direction with respect to me, it would appear shrunken in this direction because I'm measuring something from light that arrives at my eye simultaneously, which means that if it arrives at my eye simultaneously, it actually left this object at two different times. So the side that's farthest from me has to be emitted at one point in time, and the side that's on this side has to be emitted at a different point in time, and everywhere in between has to be emitted at a different point in time in between. So that when it arrives at my eye simultaneously and I can measure the width, it appears to be squished in some direction. And the way that it appears is the way that it is. This is the shape that object would have as it's moving from my reference frame. If you were standing in its reference frame right here, then it would be round again. So this shows up, for example, in like time dilation. Is time dilation a real thing, or is it just something that we talk about because because of reasons? The answer is it's a real thing. Time dilation is a real phenomenon. It was first demonstrated, I believe it was first demonstrated, by looking at muons in the upper atmosphere. So cosmic ray comes in, hits the upper atmosphere, creates a shower of particles in the upper atmosphere. Some of those particles are called muons. Muons have a lifetime. So the lifetime of a muon is about 2 microseconds. So that's 2 times 10 to the minus 6 seconds. That's how long a muon lives before it spontaneously decays into an electron, plus a couple neutrinos. So muons can only live for 10 to the minus 6 seconds. We can see what the energy of these muons are, how long they should live, or like how fast they're moving. And even the super energetic ones are going to be moving at like roughly the speed of light. So it's roughly the speed of light. So you can say, okay, 2 microseconds, they form in the upper atmosphere, they come down to the surface of the Earth in 2 microseconds. If they're moving at roughly the speed of light, then they can only travel how many feet? 2,000 feet. 2,000 feet's not right. It's a foot per nanosecond. And you have 1,000 nanoseconds. And so you get 1,000 feet. 1,000 feet. Right, the speed of light is about 1 foot per nanosecond. It's 30 centimeters per second, or 30 centimeters per nanosecond, which is about 1 foot. Okay, it has a lifetime of 2 times 10 to the minus 6 seconds. That is 2,000, it's 2,000 nanoseconds. Yeah, so I did it right the first time. 2,000 nanoseconds. This is 2,000 nanoseconds, and so these muons can travel 2,000 feet. Okay, they're traveling at roughly the speed of light. They come down 2,000 feet in the atmosphere. They should disappear. In their clock, they still only live for 2 times 10 to the minus 6 seconds, 2 microseconds. But we, on the outside, here's us, we observe these muons, they form, and they actually make it down to the detectors at the surface of the Earth. So because they make it down to detectors at the surface of the Earth, that means that the lifetime that we measure must be longer than this 2 times 10 to the minus 6 seconds. And so we measure, because they are moving with respect to us, their clock is moving with respect to us, and we measure a dilated time. So our clock, we might get something like 10 to the minus 3 seconds. Okay, so we'll see that their lifetime is actually a millisecond instead of 2 microseconds, and that gives you, another factor of 1,000. So now you can go 200 or 2 million feet, which is not the thickness of the atmosphere. So these particles can make it all the way to the surface. So from our perspective, the clock on the muon slows down, and they live longer. From the muon's perspective, the muon says, no, what's actually happening is here's you on the surface of the Earth, and you're all squatty. The atmosphere is a lot thinner because the muon measures a contracted length. We are the ones that are stationary with respect to the ground. We measure the proper length, but we measure the dilated time in this scenario. The muon themselves, they're the ones that are moving, and so they measure a contracted length, and they're like, no, this atmosphere is not that thick. So you claim that the atmosphere is 2 million feet thick, for example. I'm making that number up. we claim that the atmosphere is 2 million feet thick, and this muon will actually claim that the atmosphere is only 2,000 feet thick, and so it's able to make it that 2,000 feet in its own lifetime. So these are the same. It's the same scenario, but it's viewed from two different reference frames. In one reference frame, it measures the proper time, but a contracted length. In the other reference frame, you measure the proper length and a dilated time. Okay, now back to what I was mentioning before, that you have this scenario where if you exert a force on something, forces cause change in momentum, dt, like this. That is a change in gamma mv, because this is what relativistic momentum looks like. Change in gamma mv. And so the mass is constant, and so you're looking at a change in gamma and v right here. And as you continue to exert a force, what ends up happening is that gamma v, this product, has to grow. So you're exerting a force over time, gamma v, that product has to grow. And what ends up happening is that all of that growth takes place in gamma and not in v. So if I plot, again, that plot that I showed earlier with gamma as a function of velocity, it goes like this, and then it grows up very quickly like that. So if I'm adding momentum to the system, so momentum is being added to that system as I keep exerting the force, there's a lot more momentum to gain here by increasing gamma than there is by increasing v. So as I push on it, gamma grows, gamma grows by a lot, v grows by very, very little. So if I have some amount of force that I'm going to add to the system, this is where it's all going to go. It's all going to get consumed in increasing gamma, and it's not going to go in, v will increase a little bit, but gamma increases a huge amount. So that is the behavior of gamma as you approach this asymptote, is that because it grows up to infinity, this is the reservoir that you have to store all that, impulse, I guess. So impulse is force times time. So you store all that impulse, and it goes into this gamma. That's your reservoir. So v doesn't grow very much, gamma grows by a huge amount. So that's what's going on. It's not that Newton's third law, none of Newton's laws stop working. All of Newton's laws work. The difference is that Newton's law, the way that they were formulated at Newton's time, were wrong. So Newton said that momentum was mv, but Newton was wrong. Momentum is gamma mv. And so when you increase the momentum of the system, you have to increase gamma and v. And gamma has more to grow than v does. Okay, so here's a question. Hold on. Would relativistic dilation effects also be observed in quantum stuff? For example, you have some process that goes by this quantity, or is there a potential that depends on physical distance? Would you observe differences near C? Okay, so in terms of the speed of light and the quantum wave function, you have the issue is that the group velocity has to travel. So when you have a wave, so quantum mechanical particles satisfy the wave equation. When you have a wave, the wave is going to propagate at some speed. There's a dispersion. There are two actual speeds that you can get from a wave, a type of wave, so like a water wave or a light wave or something like that. One of them call it the group velocity, v group, and the other one's called the phase velocity, which is v phase. So the phase velocity is the speed that a wavelength of a given wavelength travels, and the group velocity is let me show you what that is. All right, so you have a wave. The wave, I'll call it psi for now. It has some amplitude, and then it's got a sign, and then what's in here is a kx minus omega t. Okay, so this is the argument of the wave. This is the thing that kind of characterizes it as a wave. Omega is the oscillation frequency, and k is the wave vector, which is related to the wavelength. So the speed of the wave is omega over k. Okay, so omega has units of 1 over seconds, k has units of 1 over length, and so omega over k has units of meters per second. The other thing that you can get from this is how does this, so this is the group velocity. I believe this is the group velocity. but this depends upon. Let me verify that. Let's look that up just to make sure that I'm not lying to everybody. Group versus phase velocity. Let's see, group velocity. One of them is the slope of omega over k. Where is it? Oh, the group velocity is the slope. Yeah, okay, that makes more sense, actually. So this is the phase velocity. So let me back up here. This is the phase velocity. So the phase velocity is you have a wavelength, you have a wave with a specific wavelength and a specific oscillation frequency. That's this. Okay, so it shouldn't have been, I shouldn't have, all right, now I know better. I shouldn't make that mistake anymore. So this is a specific phase. This is a specific phase. This is a specific wavelength. It's got a specific velocity called the phase velocity. If how that velocity changes as you change from one wavelength to another is this. It's the change in omega divided by the change in this. So this is the slope of the phase velocity. So you have a bunch of phase velocities. So you have like velocity and you have omega, and you get a slope for velocities of different frequencies. So this is the velocity you get at some value. This is the velocity you get at a different value of the frequency. If all of the phase velocities are equal, then what do you get? Then the slope is zero, basically. You have the same velocity for everything. This slope, is that what I'm looking for? I think. So if you have, shouldn't have done that. Well, okay. Anyways, here we go. Like all this is going to be out here broadcast to the world. You have omega, you have k, for example. If you have something that looks like this, there we go. That gives you, in this case, each of these phase velocities is going to be that ratio. And you'll notice that the ratio is always going to give you the same phase velocity. Okay, so all of these things, omega and k, so for different wavelengths or different oscillation frequencies, you get a different wavelength. And all of them are going to, that ratio is going to be the phase velocity for each individual sized wave. So a wavelength that's this big and a wavelength that's this big are going to have the same phase velocity. If this is what's called the phase, what's this called? The dispersion relationship. So in this case, the dispersion relationship is linear, which shows that every wavelength, the ratio of every wavelength to every oscillation frequency is equal because it's got a constant slope. You can have a substance where once you get up to some point and you're trying to wiggle it at a certain speed, that it actually slows down. You know, suppose you have some substance that has some kind of viscosity or something like that. And so as you try to wiggle that substance, it might not be able to respond the same to really super fast wiggling as it does to slower wiggling. Even if you consider a guitar string, for example. So you have a guitar string for a large period of, for a variety of different wavelengths or a variety of different frequencies that you're vibrating this guitar string, it might have the same speed, but eventually you can get to the point where you fatigue the material. You're trying to vibrate it so fast that the material doesn't have time to respond. And so as a consequence, that sound wave is going to propagate more slowly down the string than something that's vibrating more slowly. And so you can reach the physical limitations of the medium that you're propagating through. So so what can happen is, in this case, you have a dispersion relation that turns over. So it might go something like that, where as you increase the frequency here to higher and higher frequencies, the wavelength doesn't change as much. So this curvature in the dispersion relation shows up here. This is the group velocity. So the group velocity is the slope of the phase velocity. And the way that relativity works in quantum mechanics is that it's the group velocity that transmits the information. And so the group velocity is always traveling slower than the speed of light, where the phase velocity can actually have a variety of things. You can have phase velocities that do all sorts of weird things in your system. It's the group velocity that matters the most. So I think there's, in this Wikipedia article, it shows you can have examples of things where you have two things that are moving in a particular direction, two phases that are moving in a particular direction, but the group is actually moving in the opposite direction. I have a Mathematica notebook that shows this as well. So here's an example of 3 phases that are moving in a particular direction, and here's the group. Let's see if it shows one where the phase velocity is moving at a different rate than the group velocity. It doesn't seem to be showing it up or showing that. Oh, so here's one. So the green circles propagate with the group velocity. So that's this moving with the group velocity. You can see this on this particular wave that's shown here. The group is basically the envelope. It's the sum of all the phases. And you can see that those things are propagating at some rate. So here's this thing moving along. And the group velocity is shown by the motion of these green points. And this is basically what my animation does. I have an animation where you can adjust the sliders and actually see all the things that happen. The phase velocity is the phase of one specific wavelength. And so that's shown by the red square. So the red square is moving at the phase velocity. You see that it moves up here, but then it disappears. And then it comes out the other end. And the ensemble of all of these phases moving together, this is multiple phases that are added up to produce this. The ensemble moves at the slower rate of the green dots. That is the thing that is limited by the speed of light, is the group velocity in quantum mechanics. Okay, back to this. So we have, here's this thing, forces, we did this dp/dt. We know that that actually goes into changing gamma instead of changing the, well, it goes primarily into changing gamma. You get small changes in the velocity and huge changes in gamma. And so that's your reservoir. So Newton's formulation originally was that momentum was mv, and this was an incorrect formulation. It was a formulation that applies under certain conditions, specifically with gamma, when you have gamma much, much, much less than infinity, or let me say that, let me do that a little bit differently. If you have velocities that are much, much less than the speed of light, then this is correct, or correct enough. But when the velocities approach the speed of light, then this is no longer correct. So let's take an example. When does this apply? So if we have 1 over gamma is equal to 1 over the square root of 1 minus v squared. And we have v much, much less than 1, right? That's velocity much, much less than the speed of light. This, another way to write this is 1 minus v squared to the 1/2, minus 1/2. Okay, so that's rewriting this in this form. When you do a Taylor expansion, when you approximate this as, you know, what's the linear approximation to this curve? So here's that curve, you know, it has this shape. What's the linear approximation down here? What line fits through that point? And you can follow the Taylor formula and you get 1, it will be a plus 1/2 because it will be minus, and then here's a minus sign, you get plus 1/2, and you have v squared, 1 plus 1/2 v squared. So this looks like a parabola down here at the bottom, which makes sense because it's a curve. Okay, but now you got v much, much less than c, and so you have this error term. So if you use Newton's approximation was that momentum was equal to mv. Well, to first order, well, actually to second order in the velocity, the actual momentum is equal to m times 1 plus 1/2 v squared. Okay. So it's gamma, it's mv, like this. Let me try that one more time. So the actual momentum, recall, is the actual momentum P is equal to gamma mv. And so P, the real thing, this is the approximation, that's Newton's approximation. The actual momentum is gamma mv, which is mv times 1 plus 1/2 v squared. Okay, this first term right there, that is mv. The second term is plus 1/2 mv cubed. And the question is now, how important is the fact that Newton was wrong? If Newton was wrong, how wrong was he? And you can do that just by calculating how big is this term right here. So I have, that term is 1/2 mv cubed. And so how big is this quantity? Well, how big are the speeds that we're talking about with Newton? So if we're talking about stuff on the Earth, you know, even supersonic jets. say supersonic jets are going to be moving at something on the order of 1,000. So how fast is the speed of light? The speed of light, not the speed of light, the speed of sound is 300 meters per second. So 3 times the speed of sound. So Mach 3 would be 1,000 meters per second. Okay, let's go to Mach 10. Mach 10 would be 3,000 meters per second. Okay, that's 3 kilometers per second. That's pretty fast, 3 kilometers per second. If you want to escape the Earth, we're talking like escape the Earth's orbital speed, we're talking about 30,000 meters per second. So let's go to there. Let's go like we're going to escape the solar system. We're going to go at 30,000 meters per second. So these are kind of the fastest speeds that we contemplate as humans, or that we achieve as humans, at least with macroscopic objects, which Newton would be the one, like that's what all Newton had in his mind were these kinds of things. How fast could you imagine firing a cannonball? Let's go with 3,000 meters per second. Okay, now we got to compare that to the speed of light. So we're looking at this ratio V over C. This is going to be 3 times 10 to the what? 1, 2, 3, 4? 3 times 10 to the 4 meters per second. And the speed of light is 3 times 10 to the 8 meters per second. So the fastest macroscopic objects that we produce are going to be traveling at 30 kilometers per second. And that is going to be, so this cancels, there's a 1 there, and I get 10 to the minus 4. That's 0.0001. Okay, so that's the size of this term that we're missing. When you use Newton's approximation, we're missing this term. And this is how big that term is. That's what, 1/100th of 1%. Okay, but we can make measurements that are better than that. However, this is V. This is V over C. We need to cube that. We have to cube that. That's 10 to the minus 4. When we cube that, that gets us 10 to the minus 12. So when we're using MV and we're talking about things that we would have near the surface of the Earth, the error that we're introducing is in the 12th decimal place for the fastest objects that we can imagine producing. So the fastest rocket ships that we make that are moving at 30,000 meters per second. The error that we introduce is in the 12th decimal place. So that's tiny. That's like negligible. Well, you know, unless you're like, we only have, our clocks measure things to the nanosecond, right? That's 10 to the 9. This is 10 to the minus 12, 10 to the minus 9. A nanosecond is 10 to the minus 9 seconds. So our clocks are measuring things like to the nanosecond with the GPS satellites. This is 10 to the minus 12. It's so far, it's 1,000 times smaller than the precision of a typical clock. Now, it might accumulate over long periods of time, but still, this is the 12th decimal place. So we don't have to, we can basically ignore it and not worry about it. There are other things that come into most physical systems that are bigger than 10 to the minus 12. Okay, so on the other hand, if you're talking about something that's close to the speed of light, you know, you're talking about a proton in a particle accelerator, then this term becomes important, and you can no longer use the approximation that we have in the original formulation of Newton's laws. So the original formulation of Newton's laws was the momentum is mv. This is only good up until this term, 1/2 mv cubed, becomes a sizable fraction of that. So you might say, well, I need to have measurements of my momentum that are good to 4 decimal places. Okay, so then you just have to say that 1/2 mv cubed is less than 0.0001. And that tells you what velocity you're limited by. Once you get the velocities bigger than whatever that quantity happens to be, so what you have your mass, you put it in here, whatever velocity that corresponds to, once you cross that velocity, then you have to take into account the fact that that actual momentum is gamma mv. Okay, so anyways, gamma mv, that's how that works. This is momentum. And so Newton's laws still apply, first law still applies, object in motion will stay in motion, constant speed in a straight line. When you exert a force on something, you change its momentum. When you have one force exerted on something, you get an equal and opposite force exerted on it. All of those things still apply. It's just, this is the definition of momentum. Now, this also changes what we mean by energy. So energy is force times a distance. If you exert a force over some distance, you get an energy. And you end up with the following equation, which is that the energy of a system is gamma mc squared. Okay. Gamma mc squared is the total energy of some particle that's moving in a reference frame. There's another way of writing this. So let me work through some of the algebra here so we can see, what else is going to come from this. So this is the energy of a particle that's moving at the speed of light, or like not the speed of light, that's moving relativistically. This is the energy. If you exert a force on that object, again, you're going to be adding stuff to gamma. You're not adding stuff to m, you're adding stuff to gamma. You're increasing gamma as you exert a force. So let's expand this out. I get energy is equal to, this is 1 over the square root of 1 minus v squared, and then I'm going to call m. Again, I'm going to set c equal to 1. Set c equal to 1. So this is gamma m. So that's the energy of the system. And let's do the same approximation. This is equal to 1 minus v squared to the 1/2 times m. Okay, I can do the same Taylor expansion, or I'm sorry, minus 1/2. This is the minus 1/2. Same Taylor expansion that I did before, and I can get E is equal to m times 1 plus 1/2 v squared. Right? So this is exactly the same Taylor approximation that I made before, where the Taylor expansion to this, you bring the power down here, you multiply that by this thing, and then you drop the power, basically. So this is what you get. All right, now I'm going to expand this again. I get m, that's m times 1, plus 1/2 mv squared. The kinetic energy, or the energy of the system, total energy of the system, is this quantity right here. So at low speeds, where v is much, much less than the speed of light, I can do this approximation. I can do this approximation where I take actual gamma and I approximate it as the first order approximation of gamma, or the lowest order approximation of gamma. And I get this. I get this m, the energy is equal to the mass. When the velocity is 0, so when the velocity is 0, the energy is equal to the mass. Okay, if I bring c squared back in, then I get the energy is equal to mc squared. That's the rest energy. Because an object has mass, it has energy. That's this term right here. Okay. This part right here, 1/2 mv squared. That's regular kinetic energy that everybody knows and loves from their high school physics class. Even if they didn't like high school physics class like me, you get over it and you learn in college that, okay, high school physics wasn't so bad, and you get 1/2 mv squared. That's kinetic energy. That comes from this first approximation, the lowest order approximation to this curve, the gamma curve, basically. So impulse is simply, so the question is, what is impulse? Never quite grasped the concept. Impulse is it's force times time, right? It's the change in momentum is the impulse. A change in energy is work. A change in impulse, or a change in momentum, is impulse. Why do physicists reuse the same Latin letters? Because there's so many amazing concepts in physics that we just have to double and triple up on the letters that we use. That's just the way that things go. All right, so this is where kinetic energy comes from. It's relativity. Kinetic energy fundamentally comes from relativity. That when you do the correction, you have small velocities, you have the mass that dominates. This totally dominates. The rest energy of an object way by far dominates over the kinetic energy that you get, right? Because this is mc squared. This is mv squared over c squared. So this thing is way, way bigger than that thing right there. Okay, what else? Another way to formulate energy, you can rewrite this. You can do some algebra on this thing. And you end up with, okay, what do I have? I have E equals gamma mc squared. Let's see if I can do this derivation. I've never tried to do this derivation before, so we're going to try it now. If I square the energy, I get E squared is equal to gamma squared m squared c to the 4th. Does this help me at all? That gives me, it doesn't really help me at all. Okay, so I'm sure there's a way to do it. It's probably not all that interesting. So this is one way of formulating the total energy of a system, is this gamma mc squared. Another way of formulating the total energy of the system, it has to do with, you expand gamma as the square root of 1 minus v squared over c squared. You square both sides, you get a 1 minus v squared over c squared here. You multiply a bunch of things around, and you end up with the following relationship. E squared equals basically m squared plus p squared. Okay, so the expanded version of this that includes c is going to be mc squared plus pc squared, like this. Okay, this is an equivalent representation of this equation. So these two things are actually equal to each other. You can arrive at them through different means, and you can show that one is equivalent to the other, but we won't do that here because that's what the textbook is for. Okay, so gamma mc squared right here, you have E squared equals mc squared plus pc squared. So this is basically the mass energy that you have, and this is the kinetic energy, because kinetic energy is related to the momentum. And the total energy is the sum of the mass energy and the kinetic energy. Another way to think about this, is the following way. You have energy, E squared equals m, I'm just going to do the shortened version, plus p squared. That means this. So you have momentum on this axis, you have mass on this axis, momentum on one axis, mass on the other axis, and the total energy is the hypotenuse of this triangle. So there's your momentum, here's your mass energy, and the total energy is the hypotenuse of that triangle. It's the magnitude of the vector connecting these two things. So that's weird. That actually tells you a few things. One is it tells you how to calculate the kinetic or the energy of a photon. A photon has no mass, like this, so this goes to 0, and you can get the energy of the photon is the momentum of the photon. So when I basically go to the point where there's 0 mass, and I just look at the momentum of the photon, so something traveling at the speed of light has to have no mass, otherwise it can't travel at the speed of light. Something with no mass, its momentum is on this axis, and the energy is that length. Its momentum and its energy are equal to each other, or the energy is Pc. So you get, if you need to use units where c is not equal to 1, then energy is Pc, like this. So that's the energy and or the momentum of the photon. If you have one, then you can calculate the other with this. So any massless particle, that is the momentum that a photon has. I guess, this is where this comes up. Is you may be asked the question, what is the momentum of a photon? What is the momentum of an object that's moving at the speed of light? And in that case, you can't use this gamma mc squared. Gamma mv. Can't use gamma mv because v is a number that's always less than 1. And so this doesn't apply. And so you have to have an alternative formulation for the momentum of an object where the mass is equal to 0 and the velocity is equal to the speed of light. And this is how you get that. So the momentum of a photon is equal to the energy of the photon divided by the speed of light. So any object that's moving at the speed of light, its momentum is given by E over c. So that is that's that thing. Is it possible to derive this using a force, d dx? You probably can derive this using a force. We did momentum using force, or at least we showed what happens to the momentum as you apply a force. I haven't tried it with energy before. Okay, let me take a look at the book and make sure that we've covered everything. Einstein's postulates, we did that. We did simultaneity. We did relativistic addition of velocities, relativistic momentum, relativistic energy. Ooh, should we see if the text actually does relativistic velocity properly? Let's hope so. That's the thing. We got that. Gamma is very equal to 1 at low velocities. Relativistic momentum is the same as intuitive field as class momentum. Something as u approaches c. Here's that curve that I plotted. I don't see anything that shows that they're wrong. Anyway, so here's gamma mc squared, rest energy right there. This is all the stuff that we just covered. So that is pretty cool. All right, some questions. How does this relate to photon absorbed versus reflective, giving their momentum away? Okay, so you have a photon. Here's the photon. It carries some energy and some momentum with it. It's got energy plus and momentum. It's got both. Okay, the direction of that is given by the pointing vector, which is E cross B, and some, like there's a 1 over C or 1 over mu naught or something like that in here. So the pointing vector here, E cross B, that tells you the direction of the energy flow and the momentum flow of the system. So photons have energy and momentum. The momentum of a photon is given by E over c. If we want to go back to SI units, it's E over c. Another way to write this is that the momentum is h over lambda, and the energy of a photon is hc over lambda. Okay, so this is the momentum and the energy of a photon in quantum mechanics. So h is Planck's constant, c is the speed of light, and that gives you the momentum and the energy of it. So when you have a photon that's, here's a surface, you have a photon that comes in and gets absorbed by the wall, this is the amount of momentum that's absorbed by the wall. And the question, how can a photon have momentum if it doesn't have any mass? That's what I just showed with the fact that the energy is actually the sum of the squares of the momentum, the kinetic energy here, and the rest energy here. And so if you have a rest energy, you have a momentum or a kinetic energy, these two things, the quadratic, or the, what do they call it? The sum of the squares, it's got a name. It's a, what's it? The sum, the something sum. It's the, I can't remember what they call it. No, it's the sum, it's like the sum of the squares. And there's a special word for it, and it makes you sound really smart when you say it. So, but I can't remember what it is, so I must not be all that smart. It's like the quadratic sum. Maybe that's what it is. The quadratic sum of the momentum and the rest energy. So so this equation holds true all the time. And so if this goes to 0, then that's what's left over, is the kinetic energy. So it has kinetic energy only. I guess it must be the quadratic sum, but that's not, I don't remember it being that way. Thank you for that sub, I appreciate that. And it is the L2 norm, if you want to think of it that way as well. All right, let's see, what else is there with relativity here that's important? Oh, I learned something, so this is a brief aside that goes back to fluid mechanics. So I can't remember what was going on here. I forget. I think I've covered everything in relativity. So we will now apply this information as we go forward into some really cool stuff. So the next stuff that's coming up is like nuclear physics and quantum mechanics and things like that. So that's going to be cool. Going back to fluid mechanics, one of the things that we saw in fluid mechanics was that the pressure was equal to the energy density. So the pressure is the energy density, and it has, for an ideal gas, the pressure of an ideal gas is the density times kT. Okay? Pressure is energy density, right? It's you have these things that are moving in random motions, and it produces, those random motions is a kinetic energy. We describe that kinetic energy, or we characterize that kinetic energy with a quantity called temperature. And the ideal gas law is this right here, right? It's PV equals NKT, and V over N, if I move this over there, that's P equals rho KT, where this is the density. Okay, the total internal energy of an ideal gas, or any gas, it doesn't have to be an ideal gas. Let's see, is that true? Total internal energy of a substance, we'll just go with that. Total internal energy is the number of degrees of freedom over 2 times NKT. So the number of degrees of freedom is the number of different energy reservoirs that you have available to you. So if you can only move in a single line, if you have a monoatomic gas, so here's a gas like this, it can only move in a single line, then you get the energy is equal to 1/2 NKT. And N is the number of particles that you have. If it can move in 2 dimensions, so you have a 2-dimensional gas, then you get 2 over 2 NKT. And N is the number of degrees of freedom. If you have a diatomic molecule like this, like nitrogen or something like that, then you have, not only can it translate in all 3 dimensions, so that's 3, so the number of degrees of freedom here is equal to 3 for the 3 spatial dimensions, but it can also spin around 2 different axes. So plus 2 for the different spin states that you have, plus it can oscillate. And when it oscillates, not only do you get the kinetic energy of these different things, but you also get energy in the bond between them. So as you strain the bond, you store energy in the bond, the same way that if you compress a spring, you store energy in the spring. And so you get, for this vibration state, for a diatomic molecule, you get the kinetic energy of the atoms as they oscillate back and forth, and you get the bond energy, that's associated, so that's 2 more. So at high temperatures where all these modes are excited, right, you have to be able to raise the temperature up to the point where you can excite a mode. The energy of that mode is going to be given by Planck's constant times the frequency of oscillation of that mode. So how fast does it spin or how fast does it oscillate? And so if the energy that you have available to you in your reservoir is lower than the ground state, basically like the smallest excited state in the vibration mode, then you won't excite that vibration mode at all. So it only, those extra degrees of freedom only turn on once the energy is high enough for that oscillation frequency to take place. Anyways, the point being that you add all these things together. So if you have a diatomic gas at high temperatures, you have the vibration modes, you have the spinning modes, and you have the translation in all these different dimensions, and you're going to get that the energy of the system is equal to 7/2 nkt. Okay, so then the question becomes, why does the ideal gas law look like this? So pressure has units of energy density. What's so special about F equals 2? This is the actual energy density. The actual energy density would be this divided by the volume. That's the actual energy density of an ideal gas, or a gas that has a variety of degrees of freedom. So what's so special about pressure such that F is equal to 2 here, and you get, like, that basically cancels out, and you get the energy density, P, is equal to nkt over V. And I finally figured it out. And I should have figured it out a long time ago, but I'm not quite that smart, and so I finally figured it out now. And here's the answer. You have some surface, right? This is where you're going to measure that pressure, or the energy density. So you have particles that are passing through that surface or coming back this way through that surface. When you feel a pressure on something, it's because momentum is being transferred. Right? You're feeling the force that's exerted by particles that are bouncing off that wall. So here's your surface. You have particles coming in, and it could be an imaginary surface, right? Here's your imaginary surface. But the particles are going to bounce off of that imaginary surface. And how do they bounce off of it? Well, there's going to be, the whole idea here is that you have an ensemble of particles that are all bumping into each other. So there's momentum exchange at that imaginary interface that comes from the collisions of particles at the interface that you care about, at the location where you care about. So here, or another way to think about it is, okay, you actually put a physical object there, and you measure the pressure on that object. But the point is, your stuff is coming in and bouncing back off. That corresponds to a change in momentum. And in particular, it corresponds to a change in one direction. Not the band, but the one spatial direction. So there are 2 spatial directions where the momentum that this object has, so this has got momentum in all 3 directions. It's got mvx plus mvy, that's a y, this is an x, this is a y, plus mvz. Okay, and it's only going to be one of those directions that changes. So each one of these corresponds to a 1/2 kt. Each one of these different directions that it can move corresponds to a 1/2 kt in the thermal energy of the system. When you have this thing bouncing off that surface, you are changing the energy, you're changing the direction of motion of one of those components. So in this case, it'll be the z direction, right? Let's call this the z direction. So that thing comes in and it reflects off that surface, and you get a change of twice this momentum. And that right there is the kicker. So if you had a surface that actually just absorbed all the stuff that hit it, then pressure would get dropped in half. So the pressure is the effect of all these microscopic things bouncing off of some surface. 2 of these directions don't matter, right? It's only the one that gets where the reflection takes place that matters. If you have an absorptive surface, so you have some substance, you have a gas that's in there, and the particles are hitting the surface and sticking, the pressure is going to immediately be cut in half. The reason the pressure is going to be cut in half is because you're not reflecting the particles back off the surface. You're stopping them, but you're not pushing them back the opposite direction. And so that's where the factor of 2 comes in. You're stopping their momentum in one direction, and you're changing that direction in exactly equal and opposite direction. And that gives you that the pressure is equal to 2/2 nkt, rho kt. Where if you have an absorptive surface, then the pressure would go to 1/2 rho kt, which is the 1 degree of freedom, the motion, the energy that's in a particular direction. That's energy equal to 1/2 rho kt. So the energy density, the energy is equal to 1/2 nkt from the motion in that particular direction. If you absorb it from that direction, then that would be, the pressure would be this. The pressure would be this divided by the volume, that divided by the volume. But because you actually reflect off of that surface, you have to exchange twice that amount of momentum, and there's your factor of 2. And so this is something that I'd been thinking about for a while, and it finally, all the pieces fell into place. So there we go. Okay, thanks everybody for your time. I appreciate it. What's the plan? Let's see what's coming up on, so next week I have a guest on Thursday. I might have another special stream. I think there's a bunch of physicists that are gonna get together and make fun of moonfall. So that should be fun. That I don't know if that will be, that should be next week sometime. We're still trying to work out a time. I will have a guest next week on Thursday, Nicole Barbaro. She's been on here before. Let me quickly look at what the material is that's coming up. So we're going to be talking about online learning and like what did we learn over the course of the pandemic about the difference between in-person learning and online learning. So that should be pretty interesting, especially for those that are interested in pedagogy. We're going to be moving from relativity, special relativity, to quantum mechanics. So we're going to be doing quantum mechanics for a while. We're going to do atomic physics for a while. That should be pretty cool. We're going to do radioactivity. We're going to do medical imaging, and then particle physics. So that's like 5. And then some of the stuff with like the cutting edge. So that's 6 weeks. 6 weeks of material that we got coming ahead of us.